In this lecture, I'm going to introduce some special kinds of arrows in a category. Now, arrows in a category are often called morphisms, and these are special kinds of morphisms. And they're called monomorphisms, epimorphisms, and isomorphisms. So in the category of sets, it will turn out that monomorphisms are injective functions, epimorphisms are surjective functions, and isomorphisms are bijective functions. But that's only for the category of sets. In general, these have very specific meanings. So let's move on to the definitions. Now, one bit of notation I should say that if I have f, an arrow in the category C from A to B, I will use this, I will also use the notation f colon A to B, as if f were really a function from the set A to the set B. And I will also use the notation A to B, f is an arrow from A to B. So in these two notations, the category C is not mentioned. It should be implicit. Okay, so now on to the definition of a monomorphism. So an arrow f in a category from an object B to an object C is called a monomorphism if for all objects A to B, A in the category C, and arrows, let's say G comma H from A to B in C. So when I say for all, I mean for all objects A and all arrows G and H from A to B. We have that F circle G equals F circle H implies that G is equal to H. So this is an equality in arrows from A to C, and this is an equality of arrows from A to B. Okay, just to show you that this corresponds to injections. So here's a proposition that in the category set, so recall that this is the category whose objects are sets and whose arrows are functions. F A to B is a monomorphism. So a function, this would be a function from a set A to a set B, is a monomorphism if and only if F is injective. The proof is not very difficult, but I'll do it carefully nevertheless. So the thing is that, as you'll see, these things can be a little dicey in category theory. You need to actually prove things. So we'll prove it carefully. So maybe I'll just start on a fresh page. So the situation can be pictorially denoted like this. We have set A, we have a set B, and we have a set C, and we have this morphism or a function from B to C. And we have two functions, G and H from A to B. Okay, and we need to show that if F circle G is equal to F circle H, then for all G and H, then F is injective. And conversely, if F is injective, then for all G and H. Okay, so now let's start with suppose F is injective. So maybe I'll just say F and remind you that F is from B to C is injective. Let A be any set and G, H be functions from A to B. Now suppose we know that, so let G and H be functions such that, so the hypothesis, right, such that F circle G is equal to F circle H. Now we need to show that F is equal to G. So what we have is that for every element A in A, F circle G of A is equal to F circle H of A. Okay, but this is the same as F of G of A is equal to F of H of A. But since F is injective, this implies that G of A is equal to H of A. And so since this is true for every A in A, G is equal to H. So this shows that if F is injective, then F is a monomorphism. So F is a monomorphism. That's very long. So we have a abbreviation. F is monic. So this is a short way of writing F is a monomorphism. Okay, and now we've proved one way. Let's prove the converse. So for the converse, we need to start with this situation and show that F is injective, but instead what we'll do is we'll prove the contrapositive. We'll show that if F is not injective, then you can find a set A and construct functions G and H from A to B such that G is not equal to H, but F circle G is equal to F circle H. Conversely, suppose F from B to C is not injective. So what does that mean? It means that you can find points B1 and B2 in B such that F of B1 is equal to F of B2. Now take A to be a singleton set. Just one point A. Define G of, so let's define G from A to B by setting G of A is equal to B1 and H from A to B by H of A is equal to B2. Then you can see that F circle G of A is equal to F of G of A, which is F of B1, but that's equal to F of B2, which is F circle H of A. But G is clearly not equal to H because G of A and H of A are not the same. Therefore, we have that F is not monic. So we have completed the proof of this result that in the category of sets, an arrow is monic if and only if it is injective. The definition of an epimorphism is in some sense dual to the definition of a monomorphism. So F, an arrow in a category from an object A to an object B, is said to be an epimorphism. And the abbreviation for this is EPIC. If for all objects C and morphisms G, H from B to C, if G circle F equals H circle F, implies that G is equal to H. So it's very similar to the definition of monic, except that now the direction of the location of the arrows have changed. So let me draw a picture analogous to this one. So we have so if we're looking at sets, then we could draw a picture like this. And we have F from A to B, and we have G and H from B to C. And it's quite easy to show that in the category of sets, a morphism is epic if and only if it is surjective. I leave that as an exercise. I would advise you all to actually sit down and write this down. Show that a morphism in set is epic if and only if it is surjective. Okay, but these two facts, that monics are injective and epics are surjective, this is not always true, even in a category where the objects are sets and morphisms are functions. So we've seen a lot of categories where objects are sets and morphisms are functions. For example, the category of groups, the category of rings, the category of modules for a fixed string, and so on. But partly it is true. So let's formulate this theorem. So in any category where objects are sets and arrows are functions between sets, maybe with some additional conditions. For example, the category of groups, the objects, each group has an underlying set, and the group homomorphism is a function from the set underlying one group to the set underlying another group. Of course, it needs to satisfy certain more properties. It needs to preserve the identity, multiplication, and inverse, and so on. But it is such a category. Okay, all injective arrows or morphisms are monomorphisms or monic, and all surjective arrows are epic. Note that I have not claimed the converse. It in fact turns out to be false. It's not true that every monomorphism in such a category is injective, and it's not true that every epimorphism in such a category is surjective. But this part is fairly easy to prove. So actually, I don't really need to prove this separately. I've already proved it. So if you look at this proof here, so here I'm proving that in the category of sets, every injective arrow is monic. But here I have not really used any property of the category of sets. This proof here holds equally well for any category where the objects are sets and arrows are functions. If you just go through this proof again, suppose F is injective. So F could be an injective group homomorphism, but it's injective as a function. And we have G and H. They are arrows in the category, maybe in the category of groups or rings or whatever. And so they would be, satisfy some additional conditions, but they would still be functions such that F circle G equals F circle H. So this whole argument would hold in to prove the first part of this result. that all injective arrows are monic. So see proof for sets. And for surjective to epic, well, that's an exercise that I have given you. So when you work out that exercise, you should try to see that you're actually proving this theorem here. So I'll say C proofs for sets. There are categories where all monomorphisms are injective. So here's an example of such a thing. Theorem in the category of groups, which I denote group, all monomorphisms are injective. So let's try to prove this. So remember that the category group is the category whose objects are groups and whose arrows are group homomorphisms. So what we need to show is that if something is not injective, then it is not a monomorphism. So suppose that f from G to H is a homomorphism that is not injective, is a homomorphism, a group homomorphism that is not injective. So now for such a homomorphism, so recall from the theory of groups that a homomorphism is not injective if and only if its kernel is non-trivial. So if it's not injective, that means that its kernel is non-trivial. So that means that there exists an element G which is different from the identity of G, such that f of G is equal to the identity of H. So there's a non-trivial element in the kernel of F. Now I'll construct another group and two homomorphisms from it. So define H1 and H2. I already unfortunately used up this element G here. So define H1 from Z to G and H2 from Z to G by H1 of, so a homomorphism from Z to G is completely determined by the image of 1. So this is the group Z with addition as the operation. By H1 of 1 is equal to identity of G, and this one by H2 of 1 is equal to the element G. Then F circle H1 of 1 is equal to F circle H2 of 1, and both of these are equal to identity of H. And since every element in Z can be written as a sum of ones or a sum of the inverse of 1, this implies that F circle H1 is equal to F circle H2. So what we have is that F circle H1 is equal to F circle H2, but H1 is not equal to H2. Therefore, F is not monic. So not injective implies not monic, which is the same as saying monic implies injective. Therefore, in the category of group, all monomorphisms are injective. So monomorphisms are injective in the category of groups, but there are counter examples. There are other categories where monomorphisms are not necessarily injective. One of the simplest examples would be let's just the category of divisible groups. So a group is said to be divisible if you can divide in it. So if you can divide something into equal parts. So if for every element G in G, so that G can be divided into n equal parts, and for every natural number n, there exists an element H in G such that H to the n is equal to G. So for example, Q is divisible. Any rational number can be divided by an integer n. So the additive group of rational numbers is divisible, and and another example is the quotient group of the rational numbers by the integers. This is also divisible. What about groups that are not divisible? The group Z of integers is not divisible. Now let me define a subcategory of the group, the category of groups. So let D group denote the full subcategory of group whose objects are divisible groups. So this means that the objects of D group are only those groups which are divisible. However, the homomorphisms between any two objects in D group are all the group homomorphisms. That's what we mean by full subcategory. Okay, and now if we were to try to do this proof here, that in group all monomorphisms are injective, this proof would fail in D group, because here we have used the group Z, which is not a divisible group. So we would not be able to, this H1 and H2 would not be arrows in the category D group. They are only arrows in the category group. In fact, it turns out that we can find examples here of monomorphisms that are not injective. So here's so to do that, let's just first prove a small lemma from which it will become clear that not all monomorphisms are injective. So the candidate monomorphism that is not injective is the following map: F from Q to Q mod Z, just the quotient map. The quotient homomorphism. Now let A to Q G be any arrow. So this F is an arrow in D group, and let G be any arrow in D group. So in particular, that means that A is a divisible group and G is a group homomorphism. Then if F circle G is identically 0, then it implies that G is identically 0. So if F circle G, that will go from A to Q mod Z, is identically 0, then G itself, which goes from A to Q, is identically 0. Let's prove this. So suppose we'll prove the contrapositive. Suppose G is not identically 0. Okay, so recall that G is from A to Q. Let me just write down the main things here. A to Q, we have G, and we have F from Q to Q mod Z. Okay, so suppose G is not identically 0. Then that means that there exists A in A such that G of A is a non-zero rational number. Okay, now if you have any non-zero rational number, it may be an integer or it may not be an integer. But even if it is an integer, you can divide it by some sufficiently large natural number so that it is no longer an integer. So choose n, a natural number, such that GA by n is not an integer, i.e. f of GA by n is non-zero in Q mod Z. Okay, so now we'll use the fact that A is divisible. Let x belongs to A be such that x to the power n is equal to A. Because A is divisible, we can do this. And now let's look at g of x. So if we look at g of x, n times g of x. Now since g is a homomorphism, this is the same as g of x to the power n, but that is the same as g of A, and that is so that implies that g of x is g of A divided by n. So what that means is that f circle g of x is f of g of A divided by n, but f of g of A divided by n is not 0 in Q mod Z. And therefore what we have is f is not identically 0 because we found a point on which f is not 0. And so what we proved is that that if you have if f circle g is 0, then g must be identically 0. This I claim is enough to show that f is a monomorphism. So corollary, f is a monomorphism in the category D group, the category of divisible groups. And the proof, well, so what we need to show is that if f circle G is f circle H, then G is equal to H. So suppose G and H from some divisible group A to Q are group homomorphisms such that f circle G is equal to f circle H. So that's a homomorphism from A to Q mod Z. Then define alpha from A to Q by alpha of A is equal to G of A minus H of A. So this alpha is again a homomorphism. That's easy to check. So it's an arrow in D group. And what we have is, because f circle G is equal to f circle A, f circle alpha is identically equal to 0 in as a homomorphism from A to Q mod Z. Yeah, but this implies by the previous lemma that alpha is identically 0 as a homomorphism from A to Q. But that's the same as saying that G is equal to H. So what we've shown is that F is a monomorphism in the category of divisible groups. However, clearly, F is this quotient map. It has a kernel. It is not injective. So what we see is that in the category of divisible groups, not every monomorphism is injective. So what this underlines is that when you see, although in category theory, monomorphism is supposed to be akin to injective maps, and epimorphism is supposed to be akin to surjective maps. This is not exactly the case, and this underlines the importance of writing down proofs in purely category theoretic language for anything that you're going to state in general for categories. Finally, we come to the notion of an isomorphism. So F, an arrow in a category C from A to B, is said to be an isomorphism if, and this definition is much simpler than the definition of monomorphism and epimorphism. It just simply says that it has an inverse. So if there exists an arrow F inverse from B to A such that F circle F inverse, so F inverse is from B to A and F goes back from A to B, this is actually the identity arrow of B, and F inverse circle F is the identity arrow of A. So this is a much more intuitive definition, and clearly, in the category of sets, isomorphisms are precisely bijections. You've studied in set theory that invertible functions are one-to-one and onto, and so in the category of sets, isomorphisms are bijections. Now here's an easy result theorem. Every isomorphism in any category is monic and epic. The proof is very easy. Let me do it for monic. Suppose F from A to B is an isomorphism. So monic, so let's say B to C. I like my objects to be in alphabetical order. And we have G and H from A to B, such that F circle G is equal to F circle H. So what I can do is now I can pre-compose this. F inverse circle F circle G is equal to F inverse circle F circle H. But by associativity, this implies that F inverse circle F circle G is equal to F inverse circle F circle H. But by definition of F inverse, this is identity of so F inverse, so this is the identity of B. F inverse goes back to B. Yeah. Identity of B circle G is equal to identity of B circle H. But identity of B circle G by the identity axiom in category theory is G. So this implies that G equals H. So F is monic. I leave you to write down the proof that an isomorphism is epic as an exercise.